Okay, class, we're to from sensation to perception. The sensation comes in like pain. How do you perceive it? Survival depends on sensation and perception. That's the whole base of homeostasis. Maintain a constant internal environment in the face of a changing external environment. But how can you know what's going on unless you can receive the signal? Sensation, the awareness of changes in the internal and external environment. Perception, the interpretation of these stimuli. So you sense it like in a primary area, and then an association area tells you what's going on. Okay? Input comes from exterior receptors, like in the skin, or like in your bladder, intestine. Input is relayed towards the head, but it's processed along the way, like in the thalamus. So in other words, it's relayed to the head, but once you get up, particularly in the upper area of the spinal cord and the brain, there's some crude interpretation. It's just like, let's say, chief of staff for the president. Okay, so you tell him kind of a general idea why you want to talk to the president. You don't give him specifics. And then he says, oh, okay. So in other words, along the way, you get a crude interpretation. To get a more exact interpretation, the brain. Because only the brain would have the stored memory of what you're associating with. You know, an acid burn that happened 20 years ago, now you're getting another one. How would you have known it unless you had one before? How would the association area know it? Levels of neural integration, the receptor level. Okay, we talked about that. These would be the receptors. Okay, receptor. Ascending pathways. We have talked about that. This would be an ascending pathway. Okay, those ascending pathway, again, would be a tract. Perceptual level in the what? Neural cortex. So we really have done all of this. So it came in through the receptor, went up through a pathway, and then finally got here. But along the way, like for example in the thalamus, you got a crude understanding of what it was. Crude understanding. Okay, so this again is a picture. Here it comes, going up, tract, thalamus, crude interpretation, finally to the area in the cortex. See, that's that primary somatosensory cortex, that post-central gyrus we talked about. This would be it here, and it's sending it to the proper area as to where so we've already discussed that. Okay, receptors have specificity for the stimulus energy. Basically what that means is mechanoreceptors sense mechanical stuff. Visual receptors, visual. But remember what I told you earlier about closing your eyeballs, closing your lids, and pushing on it, that if you take one to the extreme, it'll turn on and experience another modality. Stimulus must be applied in the receptive field, in the area. Receptive field means where's the area, and transduction is converted to a graded potential called a receptor potential. The more you step on my foot, the harder it hurts. It's not like no pain or full pain. Okay? A lot of this is very simple. In general sensory, the receptor potential are the same. Generator potential. Okay? Afferent neuron going in, action potentials, and first node of Ranvier. Because once you get to here, once you get to the axon, then that's when you start the action potentials. Once you get to the axon, up to that part, so in other words, here, you're getting a generator potential, a graded potential. Then this right here is synapse to this, to let's say a sensory. But once you get to this, then you're going to do action potentials in the first node of Ranvier. Okay. So in other words, we could say that the senses are coming in, receptive regions. So the senses, let's say, are hooked to these dendrites. Then it comes in. So let's start. So this could be hooked right here. Let's say this is a dendritic aspect. So then it's hooked here to the dendrite. It comes in, and when I get to the first node of Ranvier, Then we start action potential. So let's go again. So here you are. You a hooked receptor. Then I come in on the dendritic aspect, let's say, and then by the time I get to the first node of Ranvier, okay, which would be the first node, then, which is the, let's say, the axon hillock area, really, then we start these action potentials. And then this gives a graded potential. This gives all or none. Let me go back. This gives a graded potential, these here, because they can't do action potentials. Not in this area here. That's the dendritic area more. That's the dendritic area. Remember, but when it comes in, then once it gets here, then it can do action potentials. Well, how do you know that you're stepping on my foot harder if all I can do is action potentials? Remember what I told you, frequency of firing going to the brain. The harder you step on my foot, the faster the firing frequency of those action potentials. They can't get any higher. It's all or none. So the initial is a graded potential because you don't do action potential. The more you stimulate, the more you get a graded potential, more neurotransmitter. But once you get here, it's no longer a graded potential. Now it's action potentials, and the frequency of firing determines the degree of stimulus. Adaptation is changing in the presence of constant stimuli. Okay, what does that mean? All right, you put your clothes on. When you first put them on, you notice them, right? Right? But after a while, you don't notice them anymore. If somebody keeps squeezing your hand and it's not too hard, at first you'll notice it. Later, you may not notice it anymore. Because what the brain attempts to do is damp out stuff that's constant. So you can start thinking about some real stuff, some higher level stuff. How does it do that? That's called adaptation. How does it do that? Increase the threshold. What did I just say? Increase threshold voltage. It makes it harder to fire. So if you say, what's adaptation? That blanks out everything. That blanks out a lot of stuff that's insignificant. So you can concentrate on higher level stuff. But how does it do that? It makes it less responsible by increasing threshold of firing. So the receptor potentials decline in frequency or stop. Even here, it'll do some on adaptation. Even here, because if you keep pressing on it, it's going to run out of neurotransmitter or just fail to respond. But once you get to where you can do action potentials, you got another shot at it, because then the threshold voltage raises. So here, so in other words, how do you damp out your clothes on? How do you damp out somebody squeezing your hand, but not too hard? See, if it's too hard, you can't damp it out. The body will not allow you to damp it out. Let's think about the bladder. When you feel the urgency to go to the bathroom, if you don't, and the bladder's not too full, it'll go away, won't it? How does that happen? Because the stretch receptors, the mechanoreceptors, become inactive to it. They let it go. You see what I'm saying? That's how it damps out. Otherwise, when you needed to go to the restroom with your bladder, you'd have to go. You'd have to go right away. The only time that that wouldn't damp out if you had a spastic bladder. But now we're getting into pathophysiology. All right, let's go further. Fast adapting receptors signal the beginning or end of a stimulus. Okay? Receptors for pressure, touch, and smell. All right. So for pressure, you put the pressure, but you don't put it too hard, and then it goes away. Touch, you put it on there, so if you touch me, I'm not going to keep thinking about you touching me if it's a light touch. It's going to go away, so I can think about some more stuff. Smell, the smell comes in, and if it's a mild smell, now again, if you take it to the extreme, if it's a mild smell, you'll smell it for a while, and then it may go away, unless it's an extreme smell or unless the intensity of whatever you're smelling starts to increase. Then it can't adapt. Tonic receptors adapt slowly or not at all. Nociceptors and most proprio. Now, proprio, you don't want to adapt. Proprioreceptors determine your position in space. So if they adapted, how would you know? You'd be falling all the time. Nociceptors will. Now, we're going to talk about that. Pain receptors will, but you don't want them to turn off too much. Pain is a warning signal. So if the pain is kind of mild, you can damp it out, but primarily at the brain level. If the pain is kind of mild, you can damp it out so you can keep going. Otherwise, it would be a difficulty. Okay. A lot of this you already know just from yourself. All right. Pathways of 3 neurons conduct to upward brain regions. Let's go here. All right. So first order neurons, impulses to the second order neurons. Okay. So here we are. We're coming in from the first order. There we are. Now let's blow this up just a little bit if I possibly can. Okay. So here we are. We're coming in. That's the first one. Then we're picking up that second one, which is going to be in the spinal thalamic tract. Okay, that's the second order. Trans impulses to the thalamus. Okay, spinal thalamic. Then we pick up that from the thalamus and go to what? The somatosensory cortex we've talked about. So 1, 2, 3. We've already talked about this. Okay, let's go further. Processing. Identification depends on the specific location of the target. Adapt aspects of sensory, perceptual, ability to detect the stimulus. See, that's just crude interpretation as to where it is. Magnitude of estimation. Intensity is coded by what? Frequency of firing. So if I have pain on my thumb, how's it sent? The more pain is being sent by an increased frequency of firing because the action potentials can get no bigger. That's how you encode intensity. Spatial, identifying the site of patterns studied by 2-point discrimination tests. So where is it? Now, 2-point discrimination test, let's just say this. If you remember I told you about how we do it? If you get a protractor, like you draw circles. Now we have a fancy one. I'm saying use a protractor, but we have, and let's say you have the pencil on one end and the little sharp tip on the other. Okay, now we don't use that. We use something that has both sharp tips. But if you go and you push it all the way together, but it depends on the protractor, you really need something else that can get real close together. If you go to the anterior thigh and let's say take a hairpin, and push it real close together and just open a little bit and put it on the anterior thigh. Close your eyes and somebody else has to do it. Then you say, how many points do you feel? You'll say 1. But if you take that same distance on that deal and move it to your finger, you'll say 2 because the receptors are closer. What did I just say? The receptors are closer. All right. Feature abstract, identification of more complex and several stimuli. Remember those multimodal areas in the brain where we said multiple inputs? You dropped a bottle of acid. Remember that? Quality discrimination, ability to identify submodalities of sensation, sweet or sour taste. So this is getting into fine discrimination. Pattern recognition, familiar. But how do you know it's familiar unless you've previously learned it? Okay, so again, there we are. Perception of pain. So I'm going to start another one right here.